This is Mrs. T's Chem Talk for AP Chem, and we are going to do a quick review of the Introduction to Combustion. In case you don't know me, my name is Mrs. T. I'm a chemistry teacher at Calhoun High School in Merrick, New York. So again, this is going to be the combustion analysis introduction, and in class we looked at these slides in the part of the PowerPoint, and this is just to show that this is combustion and this is a balanced equation. So we have methane, which is CH4, plus 2O2, giving us CO2 plus 2H2O. And when this equation is completely balanced, all of the atoms on each side are going to be equal to each other. So I have one C on each side. I have 4 O's on each side if I distribute my coefficients, and I have 4 H's on each side. We need to be using balanced equations in order to do these questions properly. So again, CH4 plus 2O2 yields CO2 plus 2H2O. The number of carbons on each side is equal. All of the carbons from the methane went into carbon that was part of carbon dioxide. All of the hydrogens from the methane went to the hydrogens in the water in the product. So the C to H here is 1 to 4, but the CO2 to H2O is 1 to 2. So in order to find out how much hydrogen was in the original reactant, we always need to multiply our moles of water by 2 because there are 2 H's in every 1 H2O. When we look here, if we were looking at the products of a combustion reaction, this is CO2, and I see 1, 2, 3, 4, 5, 6, 7, 8, 9 C's. Oops. And when I look, I also see, when I get to my waters, I see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 hydrogens. So if I have 9 to 24 C to H, that's like saying C9 H24. And if we reduce that, that makes the empirical formula C3 H8. So C9H24 is like 3 times C3H8, and that's what we came from. So when we started, we're working backwards with combustion. We are analyzing the amount of carbon dioxide and water to think backwards to the amount of carbon and hydrogen in the original hydrocarbon. And if I count this up, 1, 2, 3, C3, 1, 2, 3, 4, 5, 6, 7, 8, H8 was the original reactant. So the original picture that I cut up for this illustration looks like this. Now the oxygen is usually given in excess, so we don't use it as part of our math determination. That's the end of our example here, but what I want to do next is just do one more example. So I'm just going to do this into a pen, and let's say that we have, so we have a hydrocarbon, which remember hydrocarbons have only hydrogen and carbon, burned in excess oxygen, producing, or it produces 38.8 grams of CO2 and 31.7 grams of H2O, and that was collected in the analysis. And the question says, find the empirical formula. We remember that if it's a hydrocarbon, it's only C's and H's. If it's burned in excess oxygen, it's combined with some amount of O2, and the two products, sorry about the bell, the two products are CO2 and H2O. Now we know the number of grams of CO2 and we know the number of grams of H2O. We want to convert those amounts of grams to moles of carbon and moles of hydrogen. The ratio of carbon to hydrogen moles found in CO2 and H2O will give us the ratio of C to H in the empirical formula. And if we reduce that to the lowest whole numbers, we will get the empirical formula. So if we want to get started, we're going to do our dimensional analysis. So yes, that was just a fire drill. I'm going to get started again here. We're going to start with the amount of carbon dioxide collected, and we're going to find out how many moles of carbon that represents, because all of the carbon from the hydrocarbon, if all of it is burned, is converted into CO2. In order to do that, remember we multiply by a fraction where the numerator and the denominator are equal to each other, but in different units. So I want to get to moles of CO2, and it's already in CO2, so 1 mole is 44.01 grams. Now grams cancel, and I'm in moles of CO2. There's 1 C for every 1 CO2, so I've now gotten out of CO2, and now I'm in moles of carbon. When I multiply and divide out, I find out that that represents 0.88162 moles of C. Remember, we're ignoring significant figures here because we're just getting ratios. So we're not rounding any significant figures in combustion analysis. We're then going to do the same thing for the water and start with our 31.7 grams of H2O. We're going to get that into moles of H2O, which 1 mole of H2O is 18.02 grams. So now when we cancel the grams, we're in moles of H2O. And there are 2 H's for every 1 H2O. H2O cancels, and now when we multiply and divide, we are in moles of H. And that comes out, when you do it on the calculator, as 3.5183 moles of hydrogen. Now, we could go straight here and say C, 0.88162, H, 3.5183, but we have to have whole numbers. So in order to get whole numbers, we divide each of these by the smallest result, and we get a 1 to 4 ratio, so that the empirical formula comes out to CH4. Hopefully this helped to illustrate the process of finding the empirical formula of a hydrocarbon from combustion. It was just a repeat of all of the questions that we did on the board to introduce this concept. So if we haven't done this in class yet this year that you're looking at it, this is in the class PowerPoint and you will see it again. If we did it in class already, hopefully this helped to clarify what's in your notes and what we did on the board. Have a good day, and let me know if you need any more help. You can certainly come by to Extra Help after school or ask me questions in class about this.